Hi Math 136. This video is centered on lesson 722, which deals with finding confidence intervals. The problem that we're looking at reads, from a survey of 39 community college students, 27 said they had a job. We want to find a 90% confidence interval for the proportion of community college students who have a job. So what I want you to be aware of is that when they're asking you to find a confidence interval, they're actually asking you, essentially, give me an interval of potential proportions, because hopefully within that interval, the true population proportion is going to be found within there. So what I would encourage you to do before we actually begin is to make sure that you have something to write with. So if you need to, please pause the video and grab paper, pencil, or a notebook, and a calculator. All right, so to begin, reading through the first part of the problem, I'm noticing that they've surveyed 39 students and 27 of them had said that they had the job. We're going to count the people who say that they have a job as a success. So basically that's what we were interested in hearing. And therefore anyone who did not come back and say that they had a job would be considered a failure. And again, we're looking at this more from the perspective of, I did not get what I wanted. We're not actually passing judgment on these individuals and saying that they are failures for not having a job while also going to community college. So to kind of go through this, the first thing that I would note here is that I have enough information in order to do my sample proportion. So remember that we denote that as p hat. So remember our little baby unicorn. And again, what you want to note here is that we are going to create a ratio or a fraction. In the denominator, we're going to put in how many people we actually talked to, and then we're going to put the number of our successes in the numerator. If we do this, we get a sample proportion of 0.69. So before we begin doing a confidence interval like this, we want to make sure that we can assume that there's an approximately normal distribution. And if you recall, we would do that by working with the formula n times p, and we would also be working with n times 1 minus p. We have the stipulation that in each case, both of them have to be greater than or equal to the value of 10. If one or the other, or both, are not greater than or equal to 10, then we have to kind of step in and say, I cannot assume that this is approximately normal. So to continue with this work, n, if you recall, deals with sample size. P is going to be our population proportion. So we kind of run into a little bit of a snag here because we don't have a population proportion in this particular problem. So we have to kind of make an edit and say, well, since I don't have that, I'm going to use the next best thing, and I'm going to use p hat. So now I'm no longer going to work with the population proportion, but I will work with the sample proportion. So when we set all of this up, we have 39 times p hat, which we know is 0.69. If we do this calculation, we end up getting 26.91. And what I want you to note here is that there is a parallel here, and it is actually because it is on purpose. If we rounded this to the nearest whole value, so since we're talking about respondents, we can only really have whole values here, we would get 27. This 27 is the same 27 that is provided for us in the narrative. In certain problems, they actually tell you the number of successes. But I also don't think that it's a bad idea to go through all of these processes in order to start ingraining it in your thought processes, because you want to make sure that you have this down pat, and you're pretty new to this, so you're still learning it. Okay, so the next one, then we would do 39 times 1 minus 0.69. If we do this calculation, we end up getting 12.09, or roughly 12 people. So in this case, again, what we want to note is that 27 is greater than or equal to 10, and then 12 is greater than or equal to 10. So we can assume approximate normality. Okay, so let's keep going then. That allows us to move forward. There we go. Okay, so the next thing that we want to do is we want to work with the formula to find our margin of error. And our margin of error formula would read E. We're just using a capital E to denote margin of error. That's going to be equal to our critical value, which we use Z sub C to indicate that. And then we sometimes use our sample standard error. Or, I'm sorry, our standard error. But in this case, again, we don't have access to our population proportion. So we're going to make an edit here, and we're going to use p hats within that. So we're going to work with our sample standard error. So again, let's go ahead and label some of these things. So this is our margin of error. This is our critical value. And then this is our sample standard error. Again, the idea of sample comes in because we are working with those p hats. Okay, so we just need to go ahead and assemble this. And it's actually not, I don't think it's too bad, especially with a little bit of practice. It does become kind of habit or old hat. So I'm going to go ahead and I'm going to focus on finding our sample standard error first because that's going to require the most calculation. So I'm just going to translate everything that I have down here. So we're going to do our square root of p hat, times 1 minus p hat all over n. So from here, what we want to note here is that we have the information that we need. P hat we said was 0.69, and this is 1 minus 0.69, all over our sample size of 39. So what I would go ahead and encourage you to do is please pause the video and actually go through the calculations, and then when you are done, come back and make sure that your solution comes out to the same as mine. So hopefully you've gone ahead and done that. So my process, it shows me that I would have the square root of 0.69 times 31 all over 39. So I'm just going in those stages right now. And then if I multiply my numerator, I'm going to get 0.2139 divided by 39. Continuing down here, if I do that division, I get 0.0054846154. And this is a good point to mention that if you are doing things in stages like I am, do not round your values in the middle of your work. Only round when you are done with your calculation. Rounding in the middle could potentially remove accuracy and throw solutions off. So once we take the square root of this value, I end up getting 0.07405818892, which if I round that to the third decimal place gives me 0.74. So I'm just going to move this up a little bit more so I have some space. So we're actually ready to construct our margin of error. So we do have E, and again Z sub C, this is our critical error, and we had discussed this in class that these are actually set values. So in the case of doing a 90% confidence interval, the critical value that we're going to use is 1.645. Again, what I would encourage you to do is please go back into this lesson, and you do have a little bit, you have a little table that indicates the critical values for 90, 95, and 99% confidence intervals, respectively. We now also have our sample standard error, which is going to be that 0.074. So taking care of this multiplication, we are going to get a value of let's see here, 0.12173. And again, if I round this to the third decimal place, it's going to be around 0.122. Okay, so this value that we have here is E. Okay, so we're almost done. The next thing we want to do is actually create the confidence interval. Sorry, I was looking for a color to work with. All right, so our general setup, that's going to be p hat minus our margin of error, and then p hat plus our margin of error. So I've gone ahead and I've actually already set it up so that it looks like it's in its interval notation. Your book sometimes represents it as p hat plus or minus your margin of error. So they've gone ahead and they've just kind of like bundled it up into one thing. I'm choosing to have it kind of expanded out. So to finish this off, again, we know that p hat from our first few steps is 0.69, and we're going to subtract that 0.122, and then we're also going to take our 0.69 and add that 0.122. Finishing this up, we're going to get 0.568, and then also 0.812. So what we are saying in this case is that we are 90% confident that the true proportion, the true population proportion of college students that have jobs is somewhere in between 56.8% and 81.2%. So again, it's not going to help us pinpoint exactly where the true population proportion is, but we're just saying I'm 90% confident that it's in here somewhere. And at this stage, we're basically saying that a majority of students have jobs, because as we can see, we don't break past the 50% mark. We're well above that. I hope that this video was helpful. If you have any other questions, please let me know.